Hello students, in this video I am going to discuss about batteries, types of batteries, that is primary battery and secondary battery, and brief description of dry cell, mercury cell, lead storage battery, nickel cadmium cell, fuel cells, and last electrochemical theory of rusting. First we will discuss about what is battery. As we know, battery is actually galvanic cell, and when more than one cell are connected in series, then this is called battery. Clear? And in battery, chemical energy of the redox reaction is converted into electrical energy. But for a battery to be of practical use, it should be reasonably light, compact, and its voltage should not vary appreciably during its use. Mainly two types of batteries are there. One is primary battery, another one is secondary battery. In primary batteries, the reaction occurs only once, and after use, over a period of time, battery becomes dead and cannot be reused again. For example, very common example, dry cell. This is also known as Leclanche cell and Mercury cell. Secondary batteries. A secondary cell or battery after use can be recharged by passing current through it in the opposite direction so that it can be used again and again. Common examples are lead storage battery and nickel cadmium cell. Now we'll discuss one by one about these. First one is a dry cell. This is also known as the Leclanche cell. The cell consists of a zinc container and that act as anode. And the cathode is a carbon, that is graphite rod, surrounded by powdered magnesium dioxide and carbon. And the space between the electrodes is filled by a moist paste of ammonium chloride and zinc chloride. Actually, we are saying this is a dry cell, but it is not completely dry. We are using the moist paste of ammonium chloride and zinc chloride. You can see in this diagram. Actually, this is the outer cap, that is zinc, which is act as a cathode, and this is at the center, that is carbon rod, which will act as a cathode, and in between these two we are taking the magnesium oxide, carbon black, ammonium chloride and zinc chloride paste. Now what are the reactions taking place? At anode, zinc lose its electron and convert into Zn2 plus ion. At the cathode, manganese dioxide and ammonium ion gain these electrons and convert into these. One manganese oxide and hydroxide, and ammonia gas is liberated. Clear? Now in this case, manganese is reduced from +4 oxidation state to +3 state. This is the change in oxidation number of manganese from MnO2 to MnOOH. Clear? What happens to this ammonia? This is in gaseous form, and that's why this ammonia produced in the reaction forms a complex with Zn2 plus. Now question may be asked, what is the role of ZnCl2? This is Zn2 plus make a complex with ammonia and form this compound. And the cell has a potential of nearly 1.5 volt. You have to remember what is cathode, what is anode, what is electrolyte, and what are the reactions taking place in dry cell. Now next one is mercury cell. It is suitable for low current devices like hearing aids, watches, etc. It consists of a zinc mercury amalgam as anode and a paste of mercury oxide and carbon as the cathode. Electrolyte is paste of KOH and ZNO. Reactions are at the anode, the zinc amalgam reacts with the OH minus and forms zinc oxide H2O, liberate 2 electron, and at the cathode this is mercury second oxide along with water gain these 2 electrons and form mercury in the liquid form and again generate OH minus ion. The overall reaction is this zinc amalgam plus HgO, it will give ZnO plus Hg liquid. The cell potential is approximately 1.35 volt and remains constant during its life as the overall reaction does not involve any ion in solution, whose concentration can change during its lifetime. Clear? Actually, its shape is like a button. That's why this is also known as a button cell. Next one is These are the two. Tri-cell and Mercury cell are the primary cells. Now, secondary cell, lead storage battery. It is the example of secondary battery, commonly used in automobiles and inverters. It consists of a lead anode and a grid of lead packed with lead dioxide as cathode. Anode is lead and cathode is lead dioxide. And a 38% solution of sulfuric acid is used as an electrolyte. Now reactions are taking place when we use the battery. At the anode, Pb will convert into PbSO4, and at the cathode, PbO2 is also converting into PbSO4, which is solid. Overall reaction we can write Pb plus PbO2 plus H2SO4, it gives PbSO4 and H2O. When it's concerned, in this case, when concentration of sulfuric acid becomes less, then it is discharged. Then again we have to charge it, and on charging the reaction is reversed, and PbSO4 on anode and cathode is converted into Pb and PbO2 respectively. It means these are the reactions when we use the lead storage battery. But when we charge it, then the reverse reaction is taking place. That is PbSO4 gain the electron, convert into Pb plus SO4 2 minus. In that case, this will act as a cathode because reduction will taking place. And again in this PbSO4 will react with the 2H2 and convert into PbO2 and lose the 2 electrons. In that case, this will act as a anode. Is that clear? Actually, whatever the battery we are using, actually this is the combination of more than one lead storage cell. It is combination of this. Clear? Generally, its voltage is 2 volt, and generally 12 volt batteries in use, and that's why this is the combination of 6 lead storage cell. 6 cathode and 6 anodes are linked in a series, and we will get the lead storage battery of 12 volt. Now, nickel cadmium cell. It is also a secondary cell. It has longer life than the lead storage cell but more expensive to manufacture, and the overall reaction is Cd plus NiOH thrice converting into CdO plus NiOH twice plus H2. This is nickel cadmium cell. Fuel cells. Galvanic cells that are designed to convert the energy of combustion of fuels like hydrogen, methane, methanol, etc. directly into electrical energy are called fuel cells. And one common example is hydrogen oxygen fuel cell. The cell was used for providing electrical power in the Apollo space program. Clear? And the water vapors produced during the reaction were condensed and added to the drinking water supply for astronauts. This is the hydrogen oxygen fuel cell. Now we'll discuss the detail of this. This is the diagram of schematic diagram of the hydrogen oxygen fuel cell. In this case, electrodes we are using the porous carbon. This one is the this one, and this one the porous carbon rod is there. At anode we bubble the hydrogen gas, and at the cathode we bubble the oxygen gas, and electrolyte is concentrated aqueous sodium hydroxide. And generally catalyst is finally divided platinum or palladium metal to increase the rate of reaction. Now what are the reactions taking place at the cathode? Oxygen will gain the electron, convert into OH minus ion, and at the anode this is hydrogen in the presence of OH minus ion convert into the water and lose the electron. Overall reaction is simply combination of hydrogen and oxygen gas to give the water. This water is used for the drinking purpose. Clear? This is the diagram of hydrogen oxygen fuel cell. What are the advantage of this hydrogen oxygen fuel cell? Or simply the fuel cells. The cell runs continuously as long as the reactants are supplied. Fuel cells produce electricity with an efficiency of about 70% compared to the thermal plants, whose efficiency is about 40%. Actually, this is thermal plants. This is the conventional mode to produce electricity. By using the fossil fuels, we generate the steam. This steam rotates the turbine and electricity is produced. In this case, efficiency is very low and it is also produced a lot of smoke, which is reason for the atmospheric pollution. But in this fuel cell, that is, fuel cells are pollution free. Okay. Now corrosion. Again, very the common topic in the lower classes you discussed about the corrosion. What happens in corrosion? Corrosion slowly coats the surfaces of metallic objects with oxides or other salts of metal. Clear? Simply, we can say wasting away of the metals in the presence of moist air. This is called corrosion. Common examples are rusting of iron. You are familiar with this. Tarnishing of silver. It is the shining appearance of silver becomes black. That is called tarnishing of silver. Development of green coating on copper and bronze. These are the some example of corrosion. Now we will discuss in detail electrochemical theory of rusting. Actually, this rusting is one electrochemical phenomena. We will try to explain it. At a particular spot of an object made of iron, oxidation takes place and that spot behaves as anode. And reaction is Fe convert into Fe2 plus and lose the electron. Its spot is an anode. Now in this case, electrons released at anodic spot move through the metal and go to another spot on the metal and reduce oxygen in the presence of H plus ion. This spot behaves as cathode. Now question arises, where from these H plus ions come? H plus ions are available from H2CO3. How this H2CO3 is formed? This is formed when water vapors react with the carbon dioxide, okay, due to the dissolution of carbon dioxide from air into water. Hydrogen ions in water may also be available due to dissolution of other acidic oxides from the atmosphere. In this way, H plus ions are present in the atmosphere and these H plus ions reduce this oxygen into the water and that spot is a cathode. If we combine these two reactions, we will get this Fe plus O2 plus 4H plus gives Fe2 plus 2H2O. And now in this case, these ferrous ions, these are further oxidized by the atmospheric oxygen to ferric ions. Fe2 plus will convert into Fe3 plus, which comes out as a rust. When this Fe3 plus react with the water and it form a rust, and rust is a hydrated ferric oxide Fe2O3 dot XH2O and with further production of hydrogen ions. The reaction may be represented as Fe2 plus 2H2O plus half O2. Fe2 plus will convert into Fe3 plus in the presence of this oxygen. Then this Fe3 plus react with the oxygen and water and form Fe2O3 plus 4H plus. This is the electrochemical theory of rusting. Diagram, you can represent this. Now in case this is the anode, this spot is anode, this lose the electron, this is lose the electron, and these electrons combine with this oxygen in the presence of H plus ion and form this water. Then these Fe2 plus atmospheric oxygen convert into Fe3 plus and Fe3 plus combined with the oxygen and form Fe2O3, which is a rust. These are the again reactions. This is oxidation reaction, this is reduction reaction, and this is final reaction from the rust. Clear? Now how can we prevent the corrosion? Actually, corrosion is due to the reaction of metal with the water and air and other gases present in the atmosphere. If we prevent this attachment, if we prevent the attachment of this metal with the oxygen, air and other substances, then we can prevent the corrosion. One of the simplest method of preventing corrosion is to prevent the surface of metallic object to come in contact with atmosphere, and this can be done by covering the surface with paint or by some chemicals like bisphenol. Another simple method is to cover the surface by other metals like tin and zinc that are inert, either inert or react to save the object. And coating of zinc over iron, that is known as galvanization. Remember it, galvanization is coating of zinc over the iron. Another method is an electrochemical method is to provide the sacrificial electrode of another metal like magnesium and zinc. Actually, these magnesium and zinc, they sacrifice themselves and prevent the rusting of iron. Clear? And that's why they itself corrode but save the object. These are the some methods of prevention. And now this chapter electrochemistry is completed. I think you have understood. Subscribe my channel if not subscribed yet. Thank you.